Welcome back. This will be a short video lecture on section 4.4 of the textbook, a closer look at testing. Now I've divided this section into 4 parts: types of errors, significance levels, multiple testing, and finally sample size. Let's begin with types of errors. Now in this subsection we want to study errors that we can make in statistical testing. And it helps to first look at errors that we can make in medical testing. Now, medical testing and statistical testing are different, but they run on parallel tracks. In both cases, we are trying to look at evidence to see if it is strong enough to support a claim. So imagine the following scenario. We have to see if there is evidence that John has been infected by the SARS-CoV-2 virus. The null hypothesis is that John does not have SARS-CoV-2, and the alternative hypothesis is that John has SARS-CoV-2. Now we're going to apply a test, and the test can come back either positive or negative. Now let's look at 2 problems. List the 4 possible interactions between A, the status of the null hypothesis, is it true or false, and B, the result of the test, is it positive or negative? Now, there are 2 very different types of errors that can be made. One is called a false positive, and in statistical language we would call this a type 1 error. And there's also the false negative error, and in statistical language we'll call this a type 2 error. And suppose this test is screening arrivals at an airport. What do these 2 errors mean for John and for society? Let's first work part 1. So let's list the 4 possible interactions between the status of the null hypothesis, that's the presence or lack of presence of SARS-CoV-2 in John, and the result of the test. Is the test positive or negative? And we can arrange these results in a 2-way table. So in this table, the rows correspond to John's status. Does John not have CoV-2? That's row 1. Or does John have CoV-2? And I'm symbolizing this as a smiling face for the case where John does not have CoV-2, or a sad face for the case where John does have CoV-2. The test itself could come out to be positive or negative. And so this is what gives us these 4 possible interactions between John's status and the status of the test. Now, let's look at each of these 4 entries. All right. In this first cell here, we know that John does not have CoV-2, but the test has come out positive. And in the world of medical testing, this would be called a false positive test. The correlate in statistical testing would be called a type 1 error. All right, so this is a case where John does not have CoV-2, but the test is claiming that he does. The test is positive for the presence of CoV-2. All right, let's look at this cell. John does not have CoV-2, and the test is negative, and that's a valid conclusion. Going down to this cell, we can see that John does have CoV-2, and the test is indicating that. The test is positive, and that's a valid conclusion. Finally, in this cell, we see that John does have CoV-2, but the test is negative. And in medical testing, this is called a false negative test, and the correlate in statistical testing is called a type 2 error. So we can see in these 4 possible interactions that there are 2 ways to be wrong. We can have false positives, a type 1 error, or we can have false negatives, a type 2 error. Now, let's go back and look at question 2, because these 2 errors are of different types, right? There are 2 different types of errors that can be made: false positives, type 1, and false negatives, type 2. Suppose this test is screening arrivals at an airport. What do these errors mean for John and for society? Well, let's consider this error here first. This is the false positive error. John does actually not have CoV-2, but the test is coming out positive. Now, this is probably very bad news for John, because he's now going to be treated as if he does have CoV-2, which means he'll be sent someplace to quarantine for a couple of weeks, and that's going to be a rough couple of weeks for John. But this has very few implications for society, because he's being treated as if he has CoV-2, when in fact he doesn't. Now, let's think about the implications of a type 2 error or a false negative. This is in some sense much more severe in this case, because John does have CoV-2. He actually has it, but the test has come out negative, and so he will be treated as if he doesn't have SARS-CoV-2. And so the implications here are much worse for society because he will now be free to go out and interact with other people, albeit somewhat limited in a somewhat limited way. But he could potentially spread SARS-CoV-2 because he is not going to be treating himself, or he will not be treated as if he actually has SARS-CoV-2 present in his person. So the implications of a false positive and a false negative can be very different, even though they're both types of errors that can be made in this context. Now let's see how these errors in medical testing map nicely onto possible errors in formal statistical decision making. So here we have the two-way table where the reality is that either the null hypothesis is true or the null hypothesis is false, and the kind of decision we're going to make is we reject the null hypothesis or we do not reject the null hypothesis. So just as in the case of medical testing, we have the four different interactions between reality and the kind of decision we're going to make. And as before, we can have a type 1 error, and this is the case where the null hypothesis is really true, but we reject it. And we also have the type 2 error, and this is the case where the null hypothesis is really false, and we fail to reject or do not reject the null hypothesis. Now let's look at type 1 and type 2 errors in the context of a concrete example. So you'll probably remember this experiment. This is the smiles and leniency experiment. Imagine that you've been accused of an academic integrity violation, and you will have to present a dossier to a panel of judges who are going to study your case. Now, included in this dossier is a picture of yourself. And the question is this: will you get a more lenient punishment if you smile rather than present a neutral expression in your picture? So mu sub s is the mean leniency score for dossiers containing pictures with a smiling expression, while mu sub n is the mean leniency score for dossiers containing pictures with a neutral expression. And the question we have before us is mu sub s greater than mu sub n? Okay, so the null hypothesis is going to be that, in fact, these means are no different from each other. The means are the same, and the alternative hypothesis is going to be that the mean for smiling is greater than the mean for a neutral expression. In other words, it is better to smile than to have a neutral expression. You'll get a more lenient punishment. All right? Now, what we want to do is describe in this situation a type 1 error and a type 2 error. So, in a type 1 error, the null hypothesis is true, but we reject it. So in a type 1 error, the null hypothesis is true, but we reject it. Thus, we're saying that the reality is there is no difference between the mean leniency scores, right? It doesn't matter if you smile or have a neutral expression, right? But our sample produced enough evidence to cause us to support the alternative conclusion that it is better to smile than to have a neutral expression. So our sample provided us with sufficient evidence to latch on to the alternative hypothesis to support it over the null hypothesis, right? Okay, what's a type 2 error? In a type 2 error, the null hypothesis is false. There really is a benefit to smiling, but our evidence wasn't strong enough to allow us to latch on to the alternative hypothesis, to support that alternative hypothesis. And so in a type 2 error, we simply fail to reject the null hypothesis. We don't find strong enough evidence for the alternative hypothesis in our sample. So that's the meaning of a type 1 and a type 2 error in context. Our next subsection is significance levels. And as we'll see, we can relate the significance level to type 1 errors. So if we're trying to understand significance levels, the significance level alpha represents the tolerable probability of rejecting H0 when it's really true. In other words, the significance level is the tolerable probability of making a type 1 error. And I think this is best understood by looking at a concrete example. Let's look at this example. Proposition A is coming up for a vote. Let P be the proportion of voters that will vote for Proposition A. Now, let's suppose that the population is actually evenly split on Proposition A. That is, the proportion P is actually equal to 0.5, all right? What happens when we sample and test? The null hypothesis is that P is equal to 0.5 versus the alternative hypothesis that P is greater than 0.5. So let's use a random sample of size 200 and let's test at the significance level alpha equals 0.05. So here is the picture of the sampling distribution for P hat. Each dot in this dot plot corresponds to reaching into the population, randomly selecting 200 voters, and calculating the value of P hat within that sample. So that's going to be the proportion of the sample that favors Proposition A. Now what we notice is that most of the time the values of P hat are going to be hovering near 0.5, which is the true proportion of voters that favor Proposition A. But through random sampling, every now and then, we will select a sample with a large value of P hat. Each of these samples in red corresponds to a sample where P hat is so large that the p-value of this observation is below the significance level. So let me say that one more time. Every time we get one of these samples out here in red, we are looking at a sample that is so rare that the probability of it happening is less than 0.05. So in each of these cases, if we were to pull one of these samples in red, we would calculate its p-value at less than 0.05, and therefore we would reject the null hypothesis and support the alternative. And that's going to happen with probability or with frequency 0.05, exactly at the significance level. So we're going to commit a type 1 error at exactly the significance level, at exactly 5%. 5% of the time, we will commit a type 1 error. So the moral to this story is that if you really want to avoid a type 1 error, then you should set your significance level low, all right? Set your significance level low to avoid a type 1 error. Let's look at the effect of lowering the significance level in the context of a hypothesis test. So we're going to look at the smiles and leniency experiment. The null hypothesis is that the mean leniency score for smiling is the same as the mean leniency score for a neutral expression. And the alternative hypothesis is, in fact, that mu sub s is greater than mu sub n. And what we're going to do is we're going to go and look at the data, but we're going to conduct a hypothesis test at the 10%, then the 5%, and then the 1% significance levels. And we're going to see how our results change as we lower our significance level from 10 to 5 to 1. So let's take a look at the data. We're doing a randomization hypothesis test for a difference in means, and the leniency and smiles experiment, the data for that experiment is automatically loaded into StatKey. And so we can see here in gold or yellow, we can see the leniency scores for the dossiers that included the smiling expression, and in purple we can see the leniency scores for those who had dossiers that included a neutral expression. Now, just within the samples, the smile group is group 1 and the neutral group is group 2. Within the samples, we can see that, in fact, group 1 had a higher leniency score than group 2, the difference being 0.79. So group 1 is certainly on average doing better, has a higher leniency score than group 2. Now, let's see how significant that difference of 0.79 is. So we're going to generate several thousand samples here in our randomization dot plot. And what we want to do is do a right-tailed test, and we want to get the p-value of this sample difference, the 0.79. So we're going to go down here, edit this, put in our observed difference, and we can see that that observed difference, that 0.79, under the null hypothesis, should only happen about 2.2% of the time. So What's the conclusion? If we're conducting our hypothesis test at the 10% significance level, right, this p-value is considered small. It's less than alpha. And so we would reject the null hypothesis and support the alternative hypothesis, all right? If alpha is equal to 5%, our p-value here at 2.2% is still less than alpha. So even at alpha equals 5%, we're going to reject the null hypothesis and support the alternative. But if our significance level is 1%, then we're going to see that this p-value of 2.2% is greater than alpha. So at the 1% significance level, we are going to not reject. We will fail to reject the null hypothesis. So we will not find support at the 1% significance level. We will not find support for the alternative hypothesis. Now, what this example shows us is that as we lower the significance level from, say, 10% to 5% to 1%, it is becoming more difficult to reject the null hypothesis and to find support in the evidence for the alternative hypothesis. And so this raises the question, is it better to work at a 10% significance level, a 5% significance level, or a 1% significance level? And that's a question that is kind of, in some sense, outside of statistics, right? So who benefits from a 10% significance level or a 1% significance level? Now, to study this a little bit, I made up this little toy example. This is not a real example, but it's just a toy example to kind of show us the trade-offs between working at a 10% significance level and, let's say, a 1% significance level. So in this example, I've got two drugs. Chotinix is being tested to see if it is more effective than iprotria at alleviating twitching syndrome. Now, if it is found to be more effective, then it will be prescribed to thousands of people, which will be a boon for the manufacturers of Chotinix. So the manufacturers of the drug Chotinix have a vested interest in demonstrating that their drug is more effective than iprotria. Okay, so we're going to set up a little experiment. Let's imagine we've got 400 patients who are suffering from twitching syndrome, and we divide them randomly into two groups. Group 1 receives Chotinix, and Group 2 receives iprotria. And we watch these subjects over a set period of time, and then we calculate the proportion of each group that found relief from twitching syndrome, right? So let's say that within the population, P sub C represents that proportion of the population of twitching syndrome sufferers that will find relief through using Chotinix, and P sub I will be the proportion of the population of twitching syndrome sufferers that will find relief through the drug iprotria. So formally, what are we testing? The null hypothesis is that these drugs are equally effective. The value of P sub C and P sub I are the same. And the alternative hypothesis is that no, in fact, Chotinix is slightly better or better than iprotria. P sub C is greater than P sub I. So what is the effect of setting the significance level at alpha equals 10%? And what is the effect of setting the significance level at alpha equals 1%? Let's look at the data. 200 people were in the Chotinix group, and amongst those 200, 162 of them found relief from twitching syndrome, and that gives a relief proportion of 0.81. Of the 200 people that were taking iprotria during our evaluation period, 150 found relief from twitching syndrome, which gives us a relief proportion of about 0.75. And so that gives us a difference in proportions of 0.06. So the question is, what is the p-value of the observed difference in proportions? And that's the kind of question that we can answer using StatKey. So let's go to a test for a difference in proportions. I'm going to make group 1 the Chotinix group, and that's going to be 162 out of 200 found relief. And for group 2, 150 out of 200 found relief. And we can see that these numbers are consistent with our previous calculations. We've got 0.81 for group 1, 0.75 for group 2, and an observed difference of 0.06. And the question is, how rare would it be, right? How unlikely would it be to see a difference as big as 0.06 in these proportions if the null hypothesis were really true? So let's generate several thousand samples under the null hypothesis. And let's find our observed difference of 0.06. We'll do a right tail test at 0.06. And we're seeing that the p-value is 0.095, or about 9.5%. So that's the p-value of this observed difference. Now the p-value of the observed difference, p hat sub c minus p hat sub I, which is 0.06, we calculated that at roughly 9%, 9.5%. So at a 10% significance level, Chotinics can claim a significant difference in effectiveness. So clearly the 10% significance level is benefiting the drug company. At a 10% significance level, they can claim with the evidence that they have found a significant difference in effectiveness. Now, at a 1% significance level, Chotinics cannot claim a significant difference. And this may benefit the consumer because we may want Chotinics to really, really demonstrate a significant difference before they put their product on the market and claim that they have found something that is significantly better than Iprotria at curing or at least alleviating twitching syndrome. And this is especially the case if this new drug is incredibly expensive. We would want Chotinics to really demonstrate a significant difference, a significant benefit over Iprotria. So we can clearly see that the setting of this significance level, whether it be at 10% or at 1%, may depend on who benefits, right? So the main thing is that the significance level and the p-value should always be announced to everybody so that we all can understand how the analysis has been carried out. Our next topic is multiple testing. Let's look at this problem. Suppose that we are to test H0 versus HA at a 5% significance level, and let's assume that the null hypothesis is true. Now, if we conduct this test 1,000 times, each time collecting a new random sample, for approximately how many of our tests will we reject H0 and support the alternative? Now, rejecting H0 and supporting the alternative when the null hypothesis is true is a type 1 error. And we know that the significance level, this 5%, is giving us the frequency with which a type 1 error will occur. So we know that, or we can fully expect that 5% of these 1,000 trials will result in rejecting H0 and supporting HA. In other words, about 50 times in these 1,000 trials, we will expect that there will be sufficient evidence to reject the null and support the alternative hypothesis. Our last topic is sample size. And I want to look at the effective sample size. So suppose that the alternative hypothesis is true, then larger sample sizes make it easier to achieve statistical significance. And I want to study this in the context of a very silly example. So that suppose that there are two colas that are competing against each other. One is called Big Fizz and the other is called Sweet Tooth. And let's just imagine that these are the only two available colas to the public and that everybody is forced to prefer one to the other. So they may like both, but they may have a preference for one over the other. And what I want to imagine is that within the public, there is a slight preference for Big Fizz to Sweet Tooth. So let's imagine that 52% of the public actually prefers Big Fizz to Sweet Tooth. The question is this: can we use hypothesis testing to detect this slight preference for Big Fizz? So here's what I did. I had StatKey simulate sampling from this population. So I'm having StatKey reach into a population in which 52% actually prefer Big Fizz over Sweet Tooth. And I did this for samples of size 100, 500, 1,000, and 2,000. So here's what I found. When I did a sample of size 100, 51 preferred Big Fizz. When I did a sample of size 500, 256 preferred Big Fizz. For a sample of size 1,000, 514 preferred Big Fizz. And finally, for a sample of size 2,000, 1,049 preferred Big Fizz. Now, we have to imagine we're conducting this experiment not knowing what's actually happening in the population. So as the investigator, we're going to let P denote the proportion that prefer Big Fizz. And what we're going to do in each case is test the null hypothesis, which is that P is equal to 0.5. That would be the hypothesis of no preference, against the alternative hypothesis of P greater than 0.5, and that would correspond to a preference for Big Fizz. What we're going to do is conduct 4 different tests, one for each of these sample sizes, and we're going to find the p-value of the observed statistic p hat. So let's go to StatKey. We're doing a test for a single proportion. The null hypothesis is set here at p equals 0.5, and what we're going to do is edit the data. And in our first case, we had 51 out of 100 that preferred Big Fizz. So we're going to generate several thousand samples. Okay, and now we're going to take a look at the proportion that we observed. We observed a p hat of 0.51, and the question is, what's the p-value of that observation? So we're going to ask for 0.51. And what that's going to tell us is that within the under the null hypothesis, we would expect to see a p hat of 0.51 about 46.2% of the time, right? So that's a very large p hat. So let's say we're working at the 5% significance level. We're not going to reject the null hypothesis based on that evidence. All right, let's go back and edit the data. Let's look at the case where I had 256 out of 500 that preferred Big Fizz. Now, this is a p hat of about 0.512. That's not that different than the p hat that we just saw, but now remember, our sample is of size 500. Let's see what the effect of that is going to be. So we're going to generate several thousand samples under this null hypothesis. We're now going to ask for the p-value of our observed value of 0.512. And in this case, our p-value is about 31.1%. Again, at the 5% significance level, we're not going to reject H0. We're not going to find favor for the alternative hypothesis with this sample size and that proportion. Okay? All right, let's keep going. Let's edit the data. Now we're going to look at a sample of size 1,000. We had 514 that preferred Big Fizz out of the 1,000. We're going to generate several thousand samples under this null hypothesis. Our observed proportion, again, it's not changing that much. It's 0.514. Let's find the p-value at 0.514. Now we can see our p-value is this 0.196. That's 19.6%. Again, at a 5% significance level, that would not be enough to reject the null hypothesis, right? So we're still at the case where this is not enough evidence to move us to believe that Big Fizz is actually preferred. All right, let's look at one more example. Let's look at the last case where we had 1,049 out of 2,000 that preferred Big Fizz. Okay, now we're going to generate several thousand samples. Okay, in this case, our observed value was 0.525. Again, not that different from what we saw before. But now we can see that our p-value is 1.3%. Okay? So by working with larger sample sizes, each time what we're seeing is that the p-value is going down. So by the time we're generating a sample size of 2,000, we are now finding enough evidence to support the alternative hypothesis, which in this case is true, right? There really is a preference for big fizz, but in order to see that preference in the data, we had to collect a sample of size 2,000. It wasn't until we got to a generous sample size that we actually were able to detect that difference with our hypothesis test. I want to close this section with some practical considerations. So suppose, for example, we are testing whether heart rate and systolic blood pressure are correlated in patients admitted to the ICU. Sample data suggests that this correlation rho is close to zero, but it's very unlikely that this correlation is equal to zero. So as our last exercise shows us, if we create a large enough sample, we will almost certainly reject the null claim that rho is equal to zero, and will find support for the alternative hypothesis that rho is not equal to zero. But is this conclusion of any practical significance? Will this have any effect on how ICU patients are treated? So we have to remember that statistics is primarily a practical science. How do we make decisions in the face of incomplete information? Is drug A better than drug B? Is teaching method A better than teaching method B? In many cases, we can find evidence to reject the null hypothesis by collecting a large sample. But is this slight preference or slight difference that might be revealed practically significant? Now, that's a question that's outside of statistics, but it's a question that we have to always bear in mind. Is our conclusion of any practical significance? All right, with that, I will close section 4.4, and I'll see you again when we take up the topics of section 4.5. Until then, take care. Bye-bye.